Welcome you all. Welcome you all in my next lecture. So, in my last lecture I talked about double integrals, Fubini's theorem and couple of applications. Now, as I said, so I think I should start the notion of triple integrals, and then there is of course some of the properties, then change of variables, Fubini's theorem, and couple of applications I will talk about. So, you will see that in a kind of double integral, the way I have defined the notions of Riemann-Darboux integral, then the same way I will also define what is called triple integral. So, this time I will be in the 3-dimensional Euclidean space. So, if I have a function say from R3 to R, say real valued functions with domain subset of 3-dimensional Euclidean space, then I can define the notions of what is called Riemann-Darboux integral in that setting, and that in particular it is called triple integral. Even if I go for more than 3 dimension, this is called what is called multiple integral. But if I am in either R2 or R3, so that means I have kind of explicit way to look at the thing. So, that means the way I have defined like Riemann-Darboux integral for or double integral, that means I have partitions the domain and taking a Riemann sum and then taking the limit, or you can say that I have defined what is called upper sum and lower sum, and then I have defined upper integral and lower integral by partitioning the domain, and then I can conclude when my function is double integrable or Riemann integrable. The similar way, if I have a function from R3 to R, we will see the similar way, like by partitioning my domain and making a Riemann sum, and let us assume that partition goes to 0, then if the limit exists, then I will say that if the limit exists, then it is nothing but the what is called triple integral. So, the same way you can define in the multiple integral as well. Okay. So, let me just restrict myself in the triple integrals, that means I am at 3 dimensions. Then once I define my triple integral, I will talk about some of its properties. Then you see the corresponding notion of iterated integral will come, and then the natural question is when triple integral exactly equal to the iterated integral, like in the double integral setting or 2 variable setting we have seen. Similar kind of theorems will be available, and in some kind of simple domain I will talk about the what is called how to calculate the triple integral. There is a way, and then change of variable formula so is there, and at the end I will talk about couple of applications. Okay. So, as I said, so triple integral, that means triple integral of scalar valued functions of vector variable, that means corresponding to the scalar field f, which is a map some domain G subset of R3 to R. Okay. So, this is the learning outcome. So, I will try to define the notion of what is called triple integral given a function f from the domain G. I say that G is a simple solid region, nice domain in R3. So, if my function is defined on that domain, real valued functions, then the notion of triple integral I will talk about that. Then we will have the notion of what is called iterated integral, and then of course, Fubini's theorem will be there to give a relations between the triple integral and iterated integral, and at the end I will talk about couple of properties of triple integral along with couple of applications. Okay. So, now let me define the first partition of a rectangular cube. Now, you see when I talked about what is called double integral, I talked about partition of a square. So, now I am in 3 dimension. So, it is expected the common domain, if I take the like square means what, like if I have a double integral, that means I have a to b, that means I have the interval a b cross c d, right. So, that means it will give you a square in R2, but once I have a functions from R3 to R, and if I consider like in x axis I am taking a to b, okay. In y axis I am taking the interval c to d, and z axis I will have say e to f. Then it will give you a kind of cube kind of things. If you see geometrically, it will give you some. So, you will have some. So, some interval here, some interval here, and some interval here. So, it will give you some kind of cube. So, therefore, I need to know what is the corresponding partitions of this rectangular cube, because I am assuming that x running over some interval, y is running over some interval, and z is running over some closed unbounded interval. Then it will give you a rectangular cube, and then I need to partition those rectangular cube like in the partitions I have done in the context of rectangular square. Okay. So, same thing you will see. So, what I am assuming that let D be a bounded rectangular cube this time. Okay. So, what is that bounded rectangular cube? It is nothing but the collection of all x, y, z in R3, where x is running from A1 to B1, y is running from A2 to B2, and z is running between A3 to B3. So, therefore, I have x axis, y axis, z axis. X axis, x is running from A1 to B1, y is running from A2 to B2, and z is running from A3 to B3. And this together, all those points x, y, z, where x is running between A1 to B1, y is running between A2 to B2, and z is running between A3 to B3, it will give you a rectangular cube, where I assume that AK is strictly less than BK. Now, what will be the corresponding partitions of this rectangular cube? Like what is the corresponding partition in the rectangular square that I already discussed. So, if you remember, I have taken a partition of the interval AB in the x axis, and I have a corresponding interval CD in the y axis. I am taking a partitions, and then I have combined it, and that will give you a partitions in the rectangular square region, right. Now, since I have a one dimensional more, so that means I have a rectangular cube, that means one more variable is coming, and z is varying from what is called A3 to B3. So, what you have to do? You take a partitions of the interval A1 to B1, take a partition of the interval A2 to B2, and take a partition of the interval A3 to B3, and then combine it. That should be the corresponding partitions of your rectangular cube. So, what I have done? Look, consider the partition Px, Py, P suffix x means it is a partitions corresponding to the x axis. In the x axis, I have the interval A1 to B1. So, that x stands for the x variable, that means x variable in the x axis. So, that means Px stands for the partitions of the interval A1 B1, where x varies. Py stands for the partitions of the interval A2 to B2, that means where y varies, and Pz stands for the partitions of the interval where z varies, that means A3 to B3. So, you know what is the partitions of this interval A1 to B1. So, that means A1 is equal to x naught, which is less than x1, x2 up to xl minus 1 exactly equal to xl B1. This is the corresponding partitions of the interval A1 to B1. Py, that is a partition corresponding to the interval A2 to B2. So, this is A1 B1, this is A2 B2, and this is A3 B3, right. So, I have three interval. So, one interval in the x axis, another interval in the y axis, another interval in the z axis. I am taking the partitions of each interval, and I am denoting it as Px, Py, Pz, P suffix x, P suffix y, and P suffix z. Then what I am doing? I am considering the combination of this partition. That means, I am considering a partitions which is Px cross Py cross Pz. So, again it will be a partitions of D. So, last time what happened in the double integral case, you have a suppose L many partitions in the interval AB lies in the x axis, and in the y axis if I have m many partitions in the interval CD, then the partitions of the square, the small sub rectangles will consist of L times m. So, this time what will happen? I will have three partitions A1 B1, A2 B2, and A3 B3. So, therefore, the corresponding I should say sub rectangular cube. Okay. So, how many of them will be there? L times m times n, that is what I have written. So, let P be a partitions of D, which is nothing but Px cross Pi cross Pz of the partition D into L times m times n. So, L first is the number of partition points of the interval A1 B1, m is nothing but the number of partitions points in the interval A2 B2, and n is the number of partitions points in the interval A3 B3. So, if I combine together, that means if I combine the partition, consider the partition Px cross Py cross Pz, it will have L times m times n subcubes, rectangular cubes, and all those cubes actually make a partitions of my bounded rectangular cube D. Okay. So, now I think partition is clear. So, it is kind of like the parallel extension of the partitions in the rectangular region, bounded rectangular region. So, now I have a bounded rectangular cube. I have three variables x, y, z. X is running between A1 to B1, y is running between A2 to B2, z is running between A3 to B3. Now, I am considering partitions from A1 to B1, A2 to B2, and A3 B3, and I am taking the cross product. It will give you partitions of my domain bounded rectangular cube into L times m times n many subcubes. Okay. So, this is actually, I can say that this is, if I do like that, then it will be a partitions of my bounded rectangular cube D. Now, what I am doing, set I from 1 up to L, j from 1 up to m and k from 1 up to n, then what I am defining d suffix I j k, that means the subcubes I am talking about, that means it is the all those points in the domain D such that x is running from xi minus 1 to xi, that means the corresponding ith subpartitions in the interval a1 b1, y belongs to the jth subpartitions of the interval a2 to b2, and z is running between the what is called kth subinterval of the interval a3 to b3. If I take the cross product of that one, that means x, y, z, x is running from here, y is running from here, and z is running between this, then this d suffix I j k, this is actually a subcube of indices means I j k. So, that means I stands for the subinterval xi minus 1 to xi in the interval a1 to b1, j stands for the subinterval yj minus 1 to yj in the interval a2 to b2, and k, that means zk minus 1 to zk, it denotes the kth subinterval of the interval a3 to b3. So, if I do that, then d suffix I j k, it is actually subcubes in the bounded rectangular cubes D. Okay. Now, what you do, it's P your partitions, which is nothing but Px cross Pi cross Pz, which is nothing but the all d suffix I j k. That means you take all subcubes d suffix I j k. This is one of the cube where I running from xi minus 1 to xi, x is running from xi minus 1 to xi, j for j, y what is called y running from yj minus to yj, and for k, j running from zk minus 1 to zk. If I put that subcube as d suffix I j k, if I collect all those d I j k where I from 1 up to l, j from 1 up to n, and k from 1 up to n, this will give you a partitions of your bounded rectangular cube. Okay. So, now you see the parallel extension is there, like in the two dimensional setting I have a rectangular domain or rectangular region, then I am taking a partition of x, partition of y, it will give you a partitions of my rectangular region. And what is the subrectangle? This is nothing but xi minus 1 to xi cross yj minus 1 cross yj. So, that is exactly replaced by the corresponding what is called subcube. That you have just only one variable, you have extra one variable because you are in 3 dimensions. So, x, y part already taken care, so only the z part you will have to take care. So, that means one more subinterval, that means z what is called k minus 1 to zk will add up there actually. Okay. So, if I have this kind of setting, then I am saying that P is a partition of the rectangular cube D, which partitions into how many subrectangular cubes? Again, how many partitions happen in the x axis of the interval a1 b1? L many. And what about the y axis? How many partition points are there? That means m many. That means it is in the interval y, that means a2 to b2. And what about the z axis, a3 to b3? This is actually k many or n many, sorry. So, this should be actually L times m times n. That many subrectangular cubes will give a partition of my bounded rectangular cubes. So, now the partition part is clear. So, now corresponding to that partition, it is expected I can define what is called Riemann sum, and if my partition take a finer and finer partitions, if the norm of the length of the partition goes to 0, then if the limit exists, you will see similar way I can define what is called triple integral. Or you can say that make a upper sum, make a lower sum, define a upper integral, lower integral, and say that your function is integrable when your upper integral and lower integral become same. So, exactly the same way I will define. Okay, there is a picture I have given. You see, this is the x axis, this is y axis, and this is z axis. Like, so you have the bounded rectangular cubic domain. So, now if I take the partition x, so this is the partitions in the x axis. Okay, this is the partitioning point in the x axis. Okay, now this is the partitioning point in the y axis. Okay, and this is the partitioning point in the z axis. Okay, if I take the cross product of that, then it will give you a small cube actually. Okay. So, those cube will give you a sub rectangular cubes, and I denote it as d suffix I j k, which is nothing but del xi. So, which is nothing but you can write it as del xi, okay, del yj and del zk. So, this is means what? That means this is nothing but x is running from area, I think so this is the area, that means this is actually xi minus xi to xi minus 1, yj to yj minus 1, and this is zk to zk minus 1. Okay. So, if this is the case, then it is called subcube. Okay. So, that will form a partitions of your what is called rectangular cube, and then now you see corresponding Riemann or triple integral of f over the rectangular cube, how I define. Okay. So, now partition part is clear, how I make the partitions. It is very kind of parallel extension for the corresponding to the two variable setting. That means, if you have a rectangular cube, that means your x is running from a1 to b1, y is running from a2 to b2, z is running from a3 to b3, then you have to take a partitions of your interval a1 b1, a2 b2 and a3 b3, you take the cross product. That means, if corresponding to a1 b1, if you have a partition px, a2 b2 if I denote it as p suffix y, and a3 b3 if I denote it as p suffix z, you consider px cross py cross pz. If I denote it as p, this will be a partitions of your rectangular cube d, and I am defining d suffix ijk, that means the ijk sub rectangular cube. Okay, and how many that subrectangular cube will be there? L times m times n times. And how I define d suffix ijk? That is again like x running from xi minus 1 to xi, y running from yj minus 1 to yj, and z running from zk minus 1 to zk. This will give you d suffix ijk, that means the subrectangular cube. How many cubes will be there? L times m times n times, and that will be a partitions of your rectangular cube d. Okay. So, if p dijk, as I said, I from 1 up to L, j from 1 up to n and k from 1 up to n, if this is a partitions of your rectangular cube d, then the norm of the partitions, what is the norm of the partition in the two variable setting, which is nothing but the area, and this time what will happen, this is I am one dimension more, so it is expected it should be the volume. So, yes, I have written the volume of your subrectangular cube d suffix ijk, and what is the volume? I am denoting as delta of Vijk, V stands for actually volume, delta of V suffix ijk, which is nothing but the volume of the subrectangular cube dijk, running from 1 up to L, j running from 1 up to m and k running from 1 up to n. And what is this? This is nothing but del xi, del yj, del zk. And what is del xi? Which is nothing but xi minus 1. So, as I said, so this is nothing but xi minus 1 times yj minus 1 times zk minus 1. So, this is the corresponding volume. So, what you have to do? You take the volume of each subrectangular cube corresponding to the point ijk, where I running from 1 up to L, j running from 1 up to m and k running from 1 up to n, and you have to take the maximum of that, that is called the norm of the partitions, and maximum will exist because I have only finite number of points, finite number of elements are there in that set. So, if I have that one, then what I am doing? So, now I have a partitions, I have a norm of the partition notion. So, same kind of similar kind of concept that you already familiar with in the two dimensional case. This time I am just extending one variable more. So, what I am doing? So, let f be a functions d subset of R3 to R, where d is a subrectangular cube in R3. Suppose let f be a bounded function on my domain D. Now, what I am doing? Then I want to form a Riemann sum. So, that means given a D, take a partitions of this rectangular cube, and suppose my partition P is d suffix ijk, where ijk varies from 1 up to L, 1 up to m and 1 up to n respectively. Then what you do? You consider the subcube d suffix ijk and choose a point C suffix ijk. I am denoting as C suffix ijk means C suffix ijk is a point in d suffix ijk. So, I mean consider the subrectangular cube d suffix ijk and consider any point inside it. Okay. And you can form a Riemann sum. What is that? This time what is the Riemann sum? That means I varies from 1 up to L, j varies from 1 up to m and k varies from 1 up to n. What is that? Value of the function at that point Cijk times the volume of your subrectangular cube delta ijk. If this is the things, then this is corresponding the partitions or Riemann sum, I should say, Riemann sum of the functions f corresponding to the partition p. So, that is the notation. This is the Riemann sum of the function f corresponding to the partition p. So, you just consider the partitions, you make the subrectangular cube, so it is called d suffix ijk, take a point inside that subrectangular cube, let it be suffix ijk, then what you do? You take the value of the functions at Cijk times the volume of your subrectangular cube, and then you have to add all the indices I, j and k. Okay. So, this will form a what is called Riemann sum. Now, what I will define the Riemann integral as I define in the R2 setting or double integral setting. So, I will say that take a finer and finer partitions. In other words, if the norm of the partition goes to 0, if the limit exists, then I will say that my function is Riemann integral. So, that is exactly I have defined. Define the Riemann integral of f over the region D, which I denote it as triple integral over D of function f x y z times dv is nothing but limit as norm of p goes to 0, this Riemann sum, provided the limit in the right hand side, RHS stands for the right hand side, exists. The above integral is also called the triple integral of f over f. Okay. So, now I think it is clear. So, you have a functions defined on a rectangular cube. I am considering a partitions. Once I have a partitions, I am defining a Riemann sum corresponding to that partition. And how you can define it? Because your domain, suppose D is rectangular cube. So, you take a partitions, suppose D suffix I j k, where I running from 1 up to L, j running from 1 up to m and k running from 1 up to n. That means it depends upon what are the partitions points in the x axis, y axis, or corresponding to the interval a1 to b1, a2 to b2 and a3 to b3. That many points will be there, and then what you have to do, you consider any arbitrary sub rectangular cube, which I denote it as suffix d suffix I j k. Take a point from this cube, denote it as suppose c suffix I j k. Form a Riemann sum, which is nothing but sum over I times sum over j times sum over k, then value of the functions at the point c I j k times that volume of this what is called sub rectangular cube. So, in other words, each rectangular cube you consider, you take any point, then you take the evaluation of your functions at that point times volume of your sub rectangular cube, and then you sum it over all sub rectangular cube. That means you take this sum over I, j and k. That is the kind of definition of Riemann sum. Okay. So, Riemann sum is what? You have a kind of corresponding partition of your domain. Take any arbitrary sub rectangular cube, take any point. So, what you have to do? You have to evaluate your functions at that point times volume of the sub rectangular cube will be there, and then you add it over all sub rectangular cube, and that is nothing but sum over I times sum over j times sum over k, and that will give you the Riemann sums. And how I define the triple integral? I will say that take a finer and finer partitions, or in other words, if the norm of the partitions I already defined, the given a partitions, norm of the partition is nothing but maximum of the any sub rectangular cube if I take the volume. So, if I take the maximum of all those volume of sub rectangular cube, this is called the partitions. If partition goes to 0, that means if your sub rectangular cube is sinking, that means volume is decreasing. If that is the case and if the limit exists, then I will say that my triple integral exists, and this is denoted by this one. So, that is how I have defined what is called triple integral. Now, you may ask, okay, this is in terms of what is called a Riemann sum. Okay. So, now instead of Riemann sum, you can also define in terms of what is called upper sum, lower sum, all upper integral, lower integral. Like that is another way I have defined what is called double integral, that means in the two dimensional setting, like what I have done. So, again there also I have taken a partitions, there I have also taken a sub rectangular interval. Okay. There of course, in terms of Riemann sum I have defined, like take a point in that sub rectangle and then evaluate your function at that point, then take the area of the rectangle, and then you just sum it up over all sub rectangles, that means sum over I and sum over j. So, that will give you the Riemann sum, and if the partition goes to 0, that means or norm of the partition goes to 0, that will, if the limit exists of this Riemann sum, that will give you the double integral. This is one of the way. Another way is that once I have a partitions of my rectangular region, like in the two dimensional case, if you remember, I have considered two things. One is m suffix capital Ij, m suffix Ij, or small m suffix Ij. What is capital M suffix Ij? That is nothing but the supremum. Supremum of my what is called functional, yes, if I remember, yes, supremum of function in that interval, right. And I have a capital Mij, I have a small Mij, then I make a upper sum and lower sum. Okay. And then I have defined what is called upper integral and lower integral, and then I say that my function is Riemann integrable if both upper integral and lower integral they are same. So, that is how I have defined another way, Riemann-Darboux integral. So, similar way you can also define in this setting as well. So, okay. So, you have a bounded what is called rectangular cube. Now, you have a corresponding partitions, you have a sub rectangular cube is there. So, what you have to do, you take the maximum okay, maximum in that subrectangular cube of the functions f, and suppose let it denoted by, in this time since it is a subrectangular cube, so therefore it should be capital M suffix I j k, okay, that is the maximum. And what will be the minimum on that subrectangular cube of your functions? That is, I denote it as small m suffix I j k. So that means I can define in this way, okay, capital M suffix I j k, which is nothing but the supremum of f of x y z, okay, where x belongs to del suffix I j k, and you can define small m I j k, which is infimum, okay. Oh, sorry, this is the point x y z. Okay. And that is true because if I assume that my function is bounded and this is a rectangular cube, so that means supremum and infimum exists. I denote it as capital M suffix I j k, and this is small m suffix I j k. So once I have that, then you make a upper sum and make a lower sum. Then what you have to do? That means you just take capital M's, or that means supremum capital M suffix I j k times the volume of the subrectangular cube, and then you do for all subrectangular cube. That means you make a sum over I, j and k, that will give you upper sum. Similarly, you make a lower sum, that means you take the infimum, that means small m suffix I j k, and then volume of your subrectangular cube, that means delta xi, delta yi, yj and delta zk. So, and then you just sum it up over all subrectangular cubes, that means sum over I, sum over j and sum over k. That means you have an upper sum, you have a lower sum. Based on upper sum and lower sum, you define upper integral and lower integral, and then you say that your function is Riemann integrable or triple integrable, then if the upper integral and will be same as lower integral. In the same way you can define your triple integral in that way as well. But I think Riemann sum is the one of the kind of easiest way to explain how the definition of Riemann-Darboux integral in the functions from R3 to R. So that is why I have these definitions in the slides. However, if we want to extend in terms of upper sum, lower sum, or upper integral, lower integral, similar process will work in the setting of functions from some rectangular cube to R. Just you have to do it appropriate way, nothing else. You just extend similarly, okay, but definition will be same. So make a upper sum, make a lower sum, make a upper integral, make a lower integral, and you say that f is Riemann-Darboux integrable if and only if upper integral same as lower integral, and that is same as equivalent that you have a partitions, make a Riemann sums, make your norm of the partition goes to 0, that means taking finer and finer partitions. If the limit exists, then I will say that corresponding what is called integral, Riemann-Darboux integral exists, and that is sometimes called the triple integral. Okay. Just simple example. So, for example, you evaluate this triple integral. So, your integrand is x times y times z square, and this is the dv notation is there. Okay. So, or dv sometimes it is denoted as dx, dy and dz. Okay. That is in some books also available. And what is your d? D is the what is called rectangular cube, where x is running from 0 to 1. So, this is the x variable, this is the y variable, and this is the z variable. Okay. And you have to evaluate this one. You can easily do that because in the integrand you have a separating of variables, right. You have a x is separated from y is separated from z square. So, that means you just put the what is called limit. So, x is running from 0 to 1, y is running from minus 1 to 2, and z is running from 0 to 3. You just perform the integral. So, that will give you the what is called the value. You just calculate. So, x dx means x square by 2, you will have some value, and then you can take it out because this is complete, give you one constant. Then you just integration minus 1 to 2 y dy, give you one value, and then perform z square. So, since it is separation of variable, it will be very easy to calculate. That when you will have like combinations, then there you need what is called some Frobenius theorem will help you to calculate this triple integral. I will give some one example there. Okay. So, next is that, as I said, so this is the definition. So, whatever definitions I have discussed is that if I have a functions defined on a rectangular cube. Now, you may say that okay, if I have a domain which is not of the form rectangular cube, okay, say arbitrary bounded domain in R3, then how can I define what is the corresponding triple integral? So, now you go back to the similar setting as I have done in the context of R2. I have defined, initially I have defined what is called double integral if I have a bounded rectangular region. And then if I have an arbitrary bounded domain in R2, how I define? I have found somehow if I get a big rectangular bounded rectangle which contains my domain, and then I am defining a new functions f twiddle which vanishes from the domain out in the rectangle, but complement of your domain D, and in the domain you just keep the same functional value, and that is the way I have extended. So, similar kind of process it also available in the context of triple integral as well. So, if I have a bounded domain in R3, what I will do? I will get a bounded rectangular cube so that it contains my domain D, and then I will define a new function, what is I am denoting as f twiddle. F twiddle, if my point x y z is coming from the domain D, which is nothing but the value of f x y z, and if the point x y z coming from the bounded rectangular cube, but which is not a domain D, for those point I will define my function value is 0. So, look, so let D be a bounded region, okay, just bounded region, it is not bounded rectangular cube, just some bounded region in R3. Then I am defining let f be a scalar valued functions which is bounded on my domain D, which is given, this is my hypothesis. Then what I am doing? Consider a rectangular cube. Now I am considering, so suppose, so it's, I cannot draw a picture, I can draw a picture, but I am very bad at it. So suppose my this is some domain, so what I will do, some kind of very bad at it. Okay. So, so I think you should forget about that maybe. My point is that if I have a bounded domain in R3, you can have a bounded rectangular cube which contains my domain, because I am having a bounded domain, right. If I have a bounded domain, you can always found a bounded rectangular cube which contains your domain. Okay. If that is the case, since D is bounded region, so consider a rectangular cube D star which is containing, this is always possible because I am starting with a bounded domain. Then what you have to do? You define a function f twiddle x y z, which is f of x y z if x y z is coming from your domain. So, that means there is no changes of function, same function, but if the point is coming from the bounded rectangular cube, but which is not a part of the domain, then I am defining it as it is 0. In that case, it is automatic that it will not affect in the integral, right. So, therefore, if now I am defining if my new functions f twiddle its Riemann integrable over D star, which is a bounded rectangular cube, and the notions of Riemann integrable on the bounded rectangular cube I have just defined, taking a partitions, making a Riemann sum, and partition goes to 0. You can define it, you can make sense it. Then we say that f is Riemann integrable over D, and what is that? Integration over D of your functions f, which is nothing but the integral over the bounded rectangular cube of your newly defined function f twiddle. So, right hand side I have already defined, right, integration over D star f twiddle dv, because f is given, that means f twiddle you know, D star the corresponding bounded rectangular cube you got this one which contains your domain D. So, the right hand side meaning I just already explained. So, if you do the right hand side, it is exactly equal to what is called your triple integral of your functions f over the bounded domain D. And what is volume of D? Volume of D means you just integrate over domain, and in that case your what will be the integrand, integrand is the constant functions 1. Okay. So, that is the volume, it will give you, so as an applications of your triple integral, it is give you the volume of your domain D. Okay. So, this is the definitions of what is called triple integral. Okay. So, I think I should draw a picture, but though sometimes I am having difficulties. Okay. So, suppose this is my domain. Okay. So, what you do? Okay. I am trying it. Okay. Yeah, I think I have I got it. So, this is yes. Is it? So, this is a cube. This is a cube, and which contains your domain. This is your domain D, and this is actually D star. So, if I take any point x y z from here, it will the value the same f of x y z, but if I take a point here which is in the bounded rectangular cube, but which is not in here. Okay. So, therefore, I am defining it as 0, and that you can do that, as I said, because I am starting with a bounded domain in R3, you can always have the existence of bounded rectangular cube which contains your domain D. Now, take a point x y z from this bounded rectangular cube. If that point x y z is inside the domain D, you define your function as it is, that means f2 ideal of xyz is nothing but f of xyz. And if your point, suppose I am taking a point xyz from the bounded rectangular cube, but which is not a point in D, that means some point like that, then I am defining my f2 ideal of xyz is 0. Okay. So, now if your function f2 ideal is Riemann integrable over D star, that notions of Riemann integrable over bounded rectangular cube I already discussed. Okay. If that is the case, then I will say that my given function m is also Riemann integrable on my bounded domain D. Not only that, value of the triple integral or value of the Riemann integral of my functions over domain D is same as value of the Riemann integrations of my newly defined function f2 ideal over the bounded rectangular cube D star. And what about the volume is an applications. If I take the integrand function is 1, that will give you the volume. Okay. So, I think I should stop here. In my next class, I will talk about some properties of triple integrals, like properties of double integral. You will see, like if I hit it by some scalar in the integrand, scalar will come out. If I take the union of two subdomain, then whether the integral will what is called add up, or if I have some kind of estimation, suppose if f of xyz is dominated by some function g of xyz, whether the triple integral also varies. So, these are the properties, like you have seen some of the properties in the context of double integral. Similar sort of properties will also be true in the context of triple integral as well. I think in my next lecture I will talk about that. In fact, I will start about that, and then I will talk about some couple of simple domains, like in your double integral, you know that vertically simple, horizontally simple, those kind of domain you have seen. So, similar kind of simple domain I will talk about in the context of 3 dimensions, and there also you will see that I can have I can calculate my what is called triple integral in terms of what is called iterated integral, and then we will have a what is called change of variable, or change of means change of, if I have a, like if I have 2 regions, or if I have a functions, what I already discussed this one, what is this? Change of variables, yes. So, if I have change of variables, so that means I want to calculate the triple integral of my function. Suppose it is given some domain in R3, and in the suppose xyz variable is there, and suppose I have a nice transformation and I want to change it to a different triple integral with different variables, and maybe in that case it will be easy to calculate. So, those kind of things will be there, change of variables, and there should be a formula, like in the double integral we have seen in terms of Jacobian, there is a formula for the change of variable. That similar kind of things also true, or also will be true in the context of triple integral as well, and we will have some applications. So, I think in my next lecture I will start with the properties of triple integral, and nice domain if I have in the R3, then you will see using Frobenius theorem you can calculate triple integral. I think I will talk about that. I think I should stop here. Thank you.